Hello, I'm just going to go through CPAC2 planning. Okay, there's various things that you need to be able to do for CPAC2. It's probably one of the easiest things to do, but probably more complicated at first. Okay, first of all, you have to obviously describe a method and what you would do. Obviously, a clearly labeled diagram is going to help. Okay, of the apparatus. How you're going to take the data and reach a conclusion, including how you're going to derive the quantities, what the graphs are going to be appropriate, which appropriate apparatus will you use, so the resolution, i.e. the smallest measurable division on the instrument. Okay, and you're supposed to do this all without help from us. Okay, written instructions, diagrams or circuit diagrams were needed. Okay, you can undertake and record trial readings, okay, to determine suitable range and intervals. Okay, talk about how you will take readings where appropriate, how you will make and record the echoes, and evaluate the methods and suggest improvements. That comes later. And then also about safety. Okay, so here's an example. The investigation to determine the spring constant K of a steel spring. So first of all, the best thing to start with is the theory aspect of it. So we know the theory for the spring is the time period is this. Okay, so what we're going to do is, okay, we're obviously going to be looking at the constants involved, the M and the T. So what we're going to do is vary the mass M and record the average time for one oscillation, T. Now, we'll talk a bit more about this, but then we're going to plot T squared on the y-axis, M on the x-axis, and the gradient will be equal to 4 pi squared over K. So therefore, K is 4 pi squared divided by the gradient. The intercept should be 0, and the value of K can be verified using Hooke's law experiment. So here what we've done is we've set out what is needed for the theory. So then comes the apparatus. Okay, so you can draw this or you can get a picture of it and adapt it as you need to. Okay, so doing the diagram means that you can show a lot of the apparatus included without having to list everything. So we can see there's two springs here, blue tack that uses the fiducial mark. So equipment that's needed, that's in the picture. Don't repeat anything that's not needed. So a 50 gram hanger with 50 gram masses up to 600, that will become apparent. Measured with a top pan balance and the uncertainty included. The meter rule, not tool, G clamps and a slot clock with appropriate time. Then, okay, the method, outline the method. The simplest thing to say is set up the apparatus as shown, okay, and then specify something in this one. Obviously, we don't want plastic deformation. In this particular case, we want to find out where to put the fiducial mark, so we want the equilibrium position. So we let it come to rest and then put the blue tack at the fiducial mark to act as a fiducial mark. Pull the mass down no more than 5 centimeters for small oscillations and release. Using the stop clock, record the time for 20 complete oscillations. So this is a bit about the procedure that we're going to do, i.e. that means passing the fiducial mark 40 times. Repeat this 3 times and calculate the 3 averages for one oscillation. And if close, i.e. within 0.07 of a second, then carry on. If not, repeat. Reject oscillations that are not in the vertical plane. Okay, so it's quite clearly saying what would be rejected. We're saying what are the conditions for carrying on. Reduce the mass by 50 grams and repeat steps 2 to 5 until M equals 250 grams. Keep the springs the same throughout, so K is constant. So this is about what we are going to keep constant and how. This is pretty much obvious. If it's carried out in the lab over 1 hour, the temperature of the spring should be approximately constant, and so expansion is negligible due to temperature differences. That could be something that would affect it. It would unlikely. So most of the time, this is pretty obvious, but if you don't state it, then you won't get the mark. Okay, so a little bit of justification of either your choice of experiment or your choice of procedures. Well, if it turns out the spring constant is 23.5 as listed in the data book for the manufacturer for the springs that we use. So if we put two in series, we get 12 newtons per meter. That was the idea. Why? Well, we want something that's quite timeable. If you think about the oscillations that would happen on a spring that's quite stiff, there would be very, very short oscillations, and I wouldn't be able to time them. So let's just calculate. And this is what we're doing in terms of we're justifying our readings, and we're instead of taking readings, we can do the calculation. So for a mass of 0.6 kilograms, we find that 20 oscillations should be 28.1, and for m being 0.25 kilograms, the smallest to go down to 20 oscillations is 18.1. So if my reaction time is 0.2 seconds, then at worst the uncertainty is about 0.2 divided by 18.1, which is 1.1%. However, with the time in the fiducial mark, this should be smaller. So whilst I've not necessarily justified my choice of equipment, what I have done is justified my choice of method. And that's all you need to do.